Welcome to this explainer. Today, we're unpacking a fascinating new research paper from Anthropic done in collaboration with AE Studio. We are looking at a genuinely revolutionary method for installing an actual off switch for dangerous AI capabilities. If you follow the development of frontier artificial intelligence, you know that managing what these massive models know and exactly who gets to access that knowledge is one of the most pressing technical challenges we're facing right now. Let's quickly define the stakes here. Frontier AI models are essentially these massive stores of knowledge, but a lot of that information falls into a category we call dual-use knowledge. Basically, the exact same understanding of a complex topic, like virology or cybersecurity, can be utilized to either save lives or cause catastrophic harm. A researcher might use a model to help create a life-saving vaccine, while a bad actor could theoretically use that exact same capability to design a deadly pathogen. Here's the roadmap for this explainer. We'll start with the dual-use dilemma. Look at why current safeguards are falling short. Introduced Anthropic's proposed solution called GRAM. See how they actually tested it out. And finally, discuss the future of AI access.
Section 1. The dual-use dilemma, balancing safety and utility.
Developers are basically trying to pull off an impossible balancing act right now, juggling three conflicting goals. First, they desperately want to surgically block malicious access to these dual-use capabilities. But second, they still want to allow vetted, trusted researchers to use those exact same capabilities for good, like patching critical vulnerabilities in cybersecurity. And third, they have to pull all of this off without degrading the model's overall intelligence on everyday tasks. It is an incredibly difficult needle to thread. Moving to Section 2, Flaws in Current Safeguards, Why the Band-Aids Fail. The current approach beautifully illustrates the core problem we have with AI protection. Right now, companies use safeguards like refusals and classifiers. They basically train the model to act as a defensive shell and refuse harmful requests. But the knowledge? It's still inside the model. A sufficiently determined attacker can just use clever jailbreaks to bypass those defenses and grab the knowledge anyway. Now, on the flip side, we have data filtering. This completely removes the dangerous data before training even begins. It works perfectly, but man, it's a blunt instrument. If you filter it out, the AI is totally safe, but it's absolutely useless to a biosecurity lab that actually needs it. If you want one safe model for the public and one specialized model for scientists, data filtering literally forces you to train two entirely separate frontier models. You'd be spending tens or hundreds of millions of dollars twice. It's just prohibitive. Which brings us to Section 3, the GRAM solution. Gradient-routed auxiliary modules. To easily grasp what GRAM does, just picture a massive, comprehensive library. Current safeguards, that's like putting up a do not read sign on the dangerous books, a sign that hackers just ignore. Data filtering, that's literally burning the books entirely. GRAM takes a totally different approach. It places all that highly specific dual-use knowledge onto a dedicated, removable bookshelf. Depending on the user, developers can literally wield that specific bookshelf in or out. You get the safety of data filtering, but you only have to pay to build the library once. So how does this actually work under the hood? During the training process, GRAM operates by adding extra neurons to every single layer of a standard transformer architecture. When the AI reads standard, harmless text, it learns normally. But step 2 is where the magic happens. When it hits text flagged as a dual-use category, let's say advanced virology, the rules suddenly change. The general-purpose weights of the network are temporarily frozen. Only the specific, dedicated virology module is allowed to update and learn from that text. The incredible consequence of this routing is that the virology knowledge doesn't diffuse across the entire massive neural network like it normally would. Instead, it gets completely boxed into these dedicated compartments. So when training is finished, developers have a huge choice. They can simply hit delete on that specific module, completely erasing the dangerous capability from the model. Or they can leave the module exactly where it is for a vetted deployment, giving trusted scientists access to a highly capable tool.
Section 4. Testing the off switch, proving the concept.
Conceptually, it's brilliant. But does it work? The researchers ran 3 phases of increasingly realistic experiments to find out. They started small in phase 1 with a synthetic dataset of children's stories, just to see if a model could actually forget a topic by deleting a module. It worked perfectly. Phase 2 got way more realistic, training on actual web text, code, and scientific papers. Finally, in Phase 3, they scaled the whole experiment up massively, applying GRAM to models with up to 5 billion parameters, just to make sure the technique holds up as the AI gets bigger.
During that second phase, they specifically tested 4 separate dual-use domains: virology, cybersecurity, nuclear physics, and a niche programming language they used as a stand-in for malware. The results were absolutely wild. Deleting a module successfully neutralized the capability across the board. It was just as effective as if the AI had never read the data in the first place. And here's the best part: deleting these modules did not degrade the model's general performance at all. The rest of the library remained perfectly intact.
Now, this might be the most critical security finding in the entire paper. You might know that other safety techniques like post-training unlearning actually just suppress dangerous knowledge. If an attacker gets their hands on a suppressed model and feeds it a tiny bit of malicious data, boom, the model remembers everything in a recovery attack. But Graham isn't suppressing anything. The knowledge literally isn't there anymore. They found that Graham models resisted these recovery attacks just as robustly as a model that had all the dangerous data completely filtered out from day one. It's a real game changer. And this brings us to the number 16. Think about the crazy efficiency here. Because they successfully isolated 4 different dual-use domains, a single Graham trading run didn't just produce one model. It yielded a model that could be configured in 16 entirely different ways, just by toggling those 4 categories on or off. You're getting 16 highly specialized model variants for the exact price of one single training run. That completely upends the traditional, insanely expensive economics of AI safety. Finally, Section 5, the future of access, limitations, and next steps. As amazing as this is, we do have to ground ourselves in reality. Anthropic is super clear that this is early-stage science. Graham is a preliminary research technique. It's not running under the hood of the Claude model you might be using today. Also, while 5 billion parameters is large, it's nowhere near full frontier scale, which can be hundreds of billions of parameters. And right now, their evaluations are mostly measuring next token prediction, which is standard for testing, but it's not the same as evaluating performance on highly complex, multi-step, real-world tasks. I want to leave you with a really profound, provocative thought from the paper. Even with a brilliantly modular architecture like Graham, we're still staring down a massive unknown. Is the highly dangerous knowledge required to, say, build a devastating weapon fundamentally tangled up with the basic physics and chemistry required to just understand the universe? Can we ever truly separate the two? Or does extreme intelligence inherently mean walking a dangerous line? It's a massive question the AI community is going to be grappling with for years to come. Thank you so much for joining me for this explainer, and keep questioning the technology shaping our future.